Hello, my darlings. Okay, so today we're going to learn something called L'Hopital's rule for indeterminate forms. Now, there's a lot in that title that we need to explain. And yes, it is pronounced L'Hopital's, not La Hospital. Okay, it's L'Hopital. It's a French name. We'll get more than that in a minute. Now, there are 6 expressions which are considered to be indeterminate. We've seen these before. Remember, whenever we were doing limits, if we'd get 0 over 0, I always told you there was more work to do, right? And usually we would factor or we would rationalize. Well, it turns out that there is another rule we can use, and that's L'Hopital's rule. If we have the indeterminate form 0 over 0 or infinity over infinity, okay, and then there are more. 0 times infinity, 1 raised to the infinity, infinity minus infinity, infinity raised to the 0, and 0 raised to the 0. All 7 of those are indeterminate forms. We are only going to be working mostly with the first two, 0 over 0 and infinity over infinity. Now, if we are evaluating an expression of the form where we're taking the limit as x heads to a number of f of x over g of x, and we get 0 over 0 or infinity over infinity, it turns out, according to L'Hopital's rule, that this limit is the limit of the derivative of the top over the derivative of the bottom. Okay? We are only going to use this when we get 0 over 0 or infinity over infinity. So again, when we got that 0 over 0, we'd say more work to do. Well, now we can use L'Hopital's rule. Also, if we get infinity over infinity, we can use L'Hopital's rule. Okay? Now, what you're finding, L'Hopital's rule is used to find limits of the form. Limit is x heads to a number c of f of x over g of x, where the limit is x heads to c equals f of x, which is the same as the limit is x heads to c of g of x, which is 0, or when the limit of both the top and the bottom are infinity. Okay? How do we find this? We try to find the limits by traditional methods, substitution. When we do the substitution, if we get 0 over 0 or we get infinity over infinity, we're going to apply L'Hopital's rule, and we're going to take the derivative of the top, and we're going to take the derivative of the bottom, and take the limit of that quotient. Okay? Remember, we are focusing on these two forms, 0 over 0 and infinity over infinity. Now, I did mention that the name was L'Hopital. I want to address the spelling here. Okay? This is how I'm spelling it, because I have an American computer with an American keyboard. The more modern French spelling has this O with the little caret on top. We don't have that on our American keyboard, okay? And when I first learned calculus, my teacher used the spelling that was in my calculus textbook, which is the same spelling that I'm using. Now, if you look in even Wikipedia or anywhere else online, you can find that in the 17th and 18th centuries, the name was commonly spelled the way I spell it, L'Hopital. And he himself spelt his name that way. However, French spellings have changed. The silent S has been removed and replaced with a circumflex over the preceding vowel. Okay, which means this silent S is gone, and now they have that caret over the O. So again, I have an American keyboard. I can't put the circumflex on there, and that's the way he wrote it. It's how I'm going to write it. Okay, so that's just, if you ever see another professor write it differently, that's why. All right, so now we're going to try it. We're going to try a simple L'Hopital's rule for polynomials and powers. Okay, now I can see, and I'm sure you can too, that if you were to do the substitution in the bottom, 2 minus 2 is going to give us 0. So, okay, I want you not to write at the moment, okay? In the past, we would do the substitution, 3 times 2 squared minus 7 times 2 plus 2 over 2 minus 2. We'd get 0 over 0. And I'm going to tell you now, the College Board has made it very clear they do not want to see this. So I'm going to erase all this out. When I was in college, you're still not writing. When I was in college, we used to just write 0 over 0 and then apply the rule. Again, The College Board has made it very clear they do not want to see that. This is what the College Board wants you to do. The College Board wants you to write the limit as x approaches 2 of the top piece of the function. Now you're writing the limit as x heads to 2 of 3x squared minus 7x plus 2. We're going to do the substitution. 3 times 2 squared minus 7 times 2 plus 2. We're going to get, let's see, 2 squared is 4 times 3 is 12 minus 7 times 2 is 14 plus 2. That's going to give us 0. Then we're going to take the limit as x approaches 2 of the bottom piece of the function, x minus 2. That's 2 minus 2, which is 0. So we have a limit of 0 on the top, a limit of 0 on the bottom. Therefore, this is an indeterminate form. And for our sake, I'm going to put 0 over 0. And now we can say that L'Hopital's rule applies. Now that we know it applies, we can say that the limit as x approaches 2 of 3x squared minus 7x plus 2 all over x minus 2 equals the limit. Now we're going to take the derivative at the top. The derivative of 3x squared is 6x minus the derivative of 7x is 7. The derivative of 2 is 0. On the bottom, the derivative of x minus 2 is just 1, and we do substitution again. 6 times 2 minus 7 over 1, that's 12 minus 7, which is 5. We have now found the limit of that original function. It's very, very important that you realize it only works. L'Hopital's rule only works if you have an indeterminate form. If you take a look at this example, the limit as x approaches 2 of 2x plus 3, okay? This limit, when you do the substitution, you have 2 times 2 plus 3 over 2. 2 times 2 is 4 plus 3 over 2. That's 7/2. If you did L'Hopital's rule, which you're not allowed to do, but if you took the derivative at the top, it's 2, and the derivative at the bottom is 1, that would give you 2. Those are not equal because L'Hopital's rule does not apply. It only applies if the derivative at the top and the bottom are either both 0 or both infinity. Now, it does turn out that sometimes you have to repeat L'Hopital's rule, that you have to do it more than once. Just like sometimes we have a double chain rule or a triple chain rule, sometimes we have to use L'Hopital's rule more than once. Now, knowing we're in this category where we're going to use repeated uses, let's just start by writing the limit as x heads to negative 2 of the top piece of the function. And that's going to say, let's say negative 2 cubed is negative 8. Negative 2 squared is 4. Negative 8 times negative 2 is 16. And then we have minus 12. So that's going to give us 0. All right. Now the limit as x approaches negative 2 of the bottom piece of the function, which is x cubed plus 8x squared plus 20x plus 16. Now negative 2 cubed again is negative 8. Negative 2 squared is 4 times 8 is 32. 20 times negative 2 is negative 40. And then we have a plus 16. And that's going to give us negative 48 at plus 48. So we have 0. So now we have an indeterminate form. And L'Hopital's rule applies. So now we're going to say that this is going to become the limit as x approaches negative 2 of the derivative of the top. The derivative of x cubed is 3x squared plus the derivative of x squared is 2x minus the derivative of 8x is 8 and the derivative of negative 12 is 0. In the bottom, the derivative of x cubed is 3x squared plus the derivative of 8x squared is 16x plus the derivative of 20x is 20. Okay. Now, let's do this again. The limit as x approaches negative 2 of the top, 3x squared plus 2x minus 8, that's going to be negative 2 squared is 4 times 3 is 12. And a 2 times negative 2 is negative 4 and minus 8. So negative 12 plus 12 is 0. Then we're going to do the limit as x approaches negative 2 of the bottom piece, 3x squared plus 16x plus 20. Well, 3 times negative 2 squared is still 12. Then we have 16 times negative 2 is minus 32. And then we have a plus 20. 12 and 20 is 32. So when we subtract 32, we're going to get 0. And if we look at these two pieces, again, this is an indeterminate form. Zero over 0. So L'Hopital's rule applies. So now we're going to take this and we're going to have the limit as x approaches negative 2 of the derivative of the top is 6x plus 2 over the derivative of the bottom is 6x plus 16. Now, I'm pretty sure if I do the substitution here that I'm not going to get 0 this time. So let's check. 6 times negative 2 plus 2 over 6 times negative 2 plus 16. So I'm going to have negative 12 plus 2, which is negative 10, over negative 12 plus 16, which is 4, and that reduces to negative 5/2. And that, my dears, is the limit for our original function as x approaches negative 2. So the key here is, I know it's annoying and it's tedious. You have to show the limit of the top and the limit of the bottom. Do the derivatives. Take the limit of the top and the limit of the bottom. College Board has been very strict on that's what they want to see. Now there's another type here, L'Hopital's rule for transcendental functions. Remember, transcendental functions are your exponential functions, your log functions, your trig functions. It's not done any differently, okay? It's really not. We take the limit as x approaches 1 of the numerator, natural log of x minus x plus 1. We do substitution. It's the natural log of 1 minus 1 plus 1. Well, minus 1 plus 1 is 0, so we're left with the natural log of 1, but that's just 0. Now if I take the limit as x approaches 1 of the bottom, x to the 4th minus x, we get 1 minus 1, which is 0. So again, we have an indeterminate form, and L'Hopital's rule applies. So that means that this limit as x approaches 1 of the natural log of x minus x plus 1 over x to the 4th minus x is going to equal, we're going to keep the limit as x approaches 1, but now we're going to take the derivatives. The derivative of the top, so the derivative natural log of x is 1 over x, minus the derivative of x is 1, the derivative of the 1 is 0, over the derivative of x to the 4th is 4x cubed, minus derivative of x is 1. Now remember, we are not taking the derivative of the function. We are taking the derivative of the top of the function over the derivative of the bottom of the function. Okay, it's important that you know the difference. Now we're going to do substitution. 1 over 1 minus 1, that's going to give me 0. That makes me nervous. And then on the bottom, it's 4 times 1 minus 1. Oh, not so bad. That's 3. And 0 divided by 3 is 0. We have found the limit. Okay, so all the ones we've done so far have been in the indeterminate form 0 over 0. So let's try one that's not. Okay, let's look at the limit as x approaches infinity of 2x cubed minus 4x squared minus 5x minus 2 all over 3x cubed minus 12. Now I know some of you are saying, I know that answer. You're not allowed to use the shortcut. Okay, I know you can look at this and say that the highest power of x is cubed and it's the same top and bottom, so the limit should be 2 thirds, okay? But remember in pre-calculus when we taught you those shortcut rules, we weren't able to tell you why those shortcut rules work. So we're now going to be able to show you. This is why our shortcut rules work. Remember last year in pre-calc, we looked at it, we examined it, we found patterns, and we discussed it intuitively, but we weren't able to prove it solidly. But that's because we didn't have enough calculus behind us. Now we have the calculus. So here we go. If we take the limit as x heads to infinity of 2x cubed minus 4x squared minus 5x minus 2, that's a polynomial. It's a cubic polynomial with a positive leading coefficient. So it looks like y equals x. That's increasing without bound. If we look at the limit as x heads to infinity of the bottom piece, 3x cubed minus 12, that's also an odd function with a positive leading coefficient. So it looks like y equals x at the ends, and it's headed to positive infinity. This is an indeterminate form. This time it's infinity over infinity. And now we know that L'Hopital's rule applies. So we're going to take this limit, and now we're going to say that's equal to the limit as x heads to infinity, and we're going to do the derivative of the top. Derivative of 2x cubed is 6x squared, minus the derivative of 4x squared is 8x, minus the derivative of 5x is 5, and the derivative of negative 2 is 0, over the derivative of 3x cubed is 9x squared, and the derivative of 12 is 0. So that's gone. Now we're going to take a limit again. We're going to take the limit as x heads to infinity of 6x squared minus 8x minus 5. That's an even polynomial with a positive leading coefficient. So it's going to look like y equals squared on the ends. So it's increasing without bounds. We have the limit as x heads to positive infinity of the bottom 9x squared. That's also an even function with a positive leading coefficient. So again, it looks like y equals x squared at the end. So it's increasing without bound. So again, we have an indeterminate form, infinity over infinity. And now we know that L'Hopital's rule applies. And unfortunately for us, we're not done. So now we have to take this limit as x heads to infinity. Now the derivative of 6x squared is 12x, minus the derivative of 8x is 8. The derivative of 5 is 0. On the bottom, the derivative of 9x squared is 18x. Okay, now if we try to do the limit again, the limit is x heads to infinity of 12x minus 8. That's a linear function with a positive leading coefficient. It looks like y equals x at the end, so it's headed to positive infinity. The limit is x heads to infinity of 18x. Again, looks like y equals x because it's linear. It has a positive leading coefficient, so it's heading to positive infinity. Therefore, we have an indeterminate form, which is infinity over infinity, and we know that L'Hopital's rule applies. Again, for a third time, we're going to take this limit and say that the limit as x approaches infinity of the derivative of 12x minus 8 is 12 over the derivative of 18x is 18. So that's a constant, so we get 12 over 18, which is not what you thought it was going to be at the beginning. However, this does reduce to 2 over 3. Those are the leading coefficients over the leading coefficient that we had originally, that you all wanted to say, oh, I know that limit, I know that limit. And this is why that limit works, because we were allowed to use L'Hopital's rule. So now we know that the limit is x heads to infinity of 2x cubed minus 4x squared minus 5x minus 2 all over 3x cubed minus 12 equals 2/3. All right, that was fun. Let's try another one. This is going to be our last one for today, okay? So we have the limit as x heads to positive infinity of 4x squared minus 5x plus 2 over e to the 5x plus natural log of x. Now, since we're doing a L'Hopital's lesson, let's assume we need to take the limit of the top, 4x squared minus 5x plus 2. Now, this is an even function with a positive leading coefficient. It's going to look like y equals x squared at the ends, so this is headed to positive infinity. Now, the bottom is going to take a little more thought, okay? We have e to the 5x plus the natural log of x. Okay, now if you remember, e to the x gets big without bound. Natural log also gets big without bound. So they're both increasing without bound, and when we add them together, we have a limit of infinity. Because they're increasing without bound, there's no limit. So now we have, again, an indeterminate form. Infinity over infinity, and we know that L'Hopital's rule applies. Okay, so that means that this limit is going to be the same as the limit as x heads to infinity of, now the derivative of the top, 4x squared is 8x, minus the derivative of 5x is 5, over, now the derivative of the bottom. The derivative of e to the 5x is 5e to the 5x plus the derivative of natural log of x is 1 over x. Now we're going to try to take this limit. So we're going to look at the limit as x heads to infinity of the top, 8x minus 5. That's a linear function with a leading coefficient that's positive, so it's going to look like y equals x, so it's going to be increasing as we go up to the right. Then we have a limit as x heads to infinity of 5e to the 5x plus 1 over x. Now it's true that as x gets huge, this piece is going to head to 0, but this piece is going to be getting large without bound again, right? This piece is just going to keep getting bigger and bigger, and even if we're adding 0 to it, the whole thing is increasing without bound. So again, we have an indeterminate form, and L'Hopital's rule applies. Don't you love having to write this out all the time? If it's a multiple choice question on the AP exam, feel free to just write, okay, I got infinity over infinity. I'm going to do the derivative of the top and derivative of the bottom. But if you are on a free response, and I'm going to make you do it on my test so that I know you're in good habits, make sure you write all this out. So we're going to take the limit as x heads to infinity. The derivative of the top is 8 over the derivative 5e to the 5x is 5 times 5 is 25 e to the 5x plus the derivative of 1 over x, remember that's x to the negative 1, is a negative 1 x to the negative 2 or 1 over x squared. At this point, I shouldn't need to do L'Hopital's rule because the top is a constant. This is not going to get any larger or smaller. It's going to stay at 8. This piece, as x gets huge, is going to head to 0. But this piece, again, is going to get huge and head to infinity. But this is in the bottom of the fraction. If the bottom of the fraction gets bigger faster than the top, 8 over 10, 8 over 100, 8 over 1,000, 8 over 10,000, this whole thing is getting smaller and smaller and headed towards 0. So the limit here is 0. So we have that the limit as x heads to infinity of this 4x squared minus 5x plus 2 all over e to the 5x plus the natural log of x equals 0. All right, guys, that's L'Hopital's rule. So remember, L'Hopital's rule works when you have an indeterminate form, 0 over 0, or infinity over infinity. You have to show that the limit of the top and the limit of the bottom are both 0, or that they're both infinity. Then it's the limit of, you take the derivative of the top over the derivative of the bottom. All right, have a nice night. I'll see you soon.